we're going to, uh, you'll notice that I have a new background for the home slide. This is a set of spectra, um, images of spectra. The first one, number one, is a continuous spectrum, so that's like a rainbow. Sodium is the second one. Hydrogen, you can see the H alpha line over there on the right. Then there's calcium and mercury, kind of down below the lettering of our outline and stuff. So by the end of the semester, we're going to be trying to decipher these spectra, which are the observable part of quantum physics, or at least the first observed feature of quantum physics. You know, they were watching these things, or observing and photographing these back in the 1800s, but they didn't know what it was until they figured out the quantum theory of hydrogen. So H is the important one there. We're going to be talking about that. But before we do any of that, I want to hand back exams. So what I'm going to do, I'm going to pause the. All right. I have a clicker question for. Okay. Clicker. Go ahead. Clicker question. Go ahead and answer this, A or B. Multiple choice. Rachel Radigan. Go ahead and answer A for this because I have your exam. But not yet. Just get your clicker. Where you at? Go ahead and do a count. Okay, 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, actually, there's one person that answered no, and I think I know who that is. So, for those of you, can you pop this down? I'll do it. Okay, for those of you that did not get your exam, came in a little late, we'll get you at the end of class. I got them up here in alphabetical order, so it'll be easy to get your paper out of there. If you look at this slide, this image, you know, a lot of times I just put something gypsy on the slides if I don't have an image or diagram, but this one's instructive. This is a website where I looked up, this is for borosilicate glass, I believe, that I used on the exam. And I used index, or a wavelength, I believe it was 50. What did I use? On the cover page, 630. I use 636. So this website allows you to look up the index of refraction for a whole ton of different glasses, like borosilicate, glass, BK, at a whole different range of wavelengths, and it's kind of cool. So you can see the image I snapped. That little slider over there on the graph, the little red dot, it actually reads out the data point. And this one didn't have a data point for 636 nanometers, so it interpolates that, but it's still pretty good. So those were real, that was real glass that you were working with on the exam. What I handed back to you was your full exam. Now, the Scantron score you can see inside web courses. We have the printouts for you, but they're not, well, we have a PDF of the printouts. So what I'll do on the weekend is I'll print those out page by page for you guys. And then I'll distribute the printouts on Monday, okay? But you have the exam, and you have your score for the multiple choice part. And the red score on the front is something out of 6 for the written problem, which is the last page. And for some of you, I think there was only one student that went 0 for 6. Everybody else got some pointage. And if you got five, but it was tough to get all 6 points. Not many people did. But if you got 5 or 6, look at your paper. If you got 5 or 6, then give yourself a pat on the back or ask a friend to give a pat on the back. Because but only if you get a 5 or 6. Who are you? There's a lost and found there? All right, so if you got 5 or 6 on that, I was pretty generous on the diagrams, but actually to get it all the way to the correct voltage, that was a challenge. It was basically Faraday's law, which was equation or formula 9, well, Roman numeral 9 on the front, plus the definition of flux was subtended underneath Faraday's equation. That was formula 8, Roman numeral 8. So now here's what this is the distribution of scores on the entire exam. So this is Scantron plus written. All right. Now, for this, you can see that there's a lot of C's. Now, if I was to now, I don't normally give a letter grade on exams, but if I did, it would be 50% and higher D, below 50% F, 60% or higher C, 75% or higher B, 90% or higher A. All right, so there were 6, and so this is getting close to being symmetrical, or a bell curve, okay, as they say, a symmetrical bell curve. But we got a little bit more B's than we have D's, so that's good. I want to push as many people here to the upper end, because if you get a B, if you earn it, you get it. You get an A, you earn an A, you get an A. I don't curve the grades. All right. Anyway, so this one, the average on the exam was 68%, and so that's like a C. So remember, C, for me, C is from 60% to 75%. So 68% is right in the middle of that. All right. Now, the other thing that you can see inside web courses is your best 2 out of 3, which I also calculated yesterday. So if you look at best 2 out of 3, for many of you, that's exam 2 and exam 3. This is the way the letter grades stack up. Right? So this is quite a bit nicer than the previous slide. Right? Now you can see here that, first of all, nobody that's taken 3 midterms has an F on their mid. I mean, so 50% of 84 is 42 points or less. Nobody's got that. Everybody's, and 4 people are just above that with a D. Only 6 people have gotten an A on exams, so that's all right. I don't mind having tough exams. But there's a whole pile of B's and C's, and a little bit more B's than C's, and so that's all right. And this is, as I mentioned to you, that when we do the best 2 out of 3 maneuver with your exam grades, you'll see a nice benefit usually. Because usually the first 2 or 3 exams, everybody, for many people, the first exam is the stinkiest grade, simply because it's your first exam with me. You're really nervous and you don't know what to expect. But you guys have done better on exam 2 and 3. So this is mostly exam 2 and 3 talking here. But for some of you, it's, you know, it's not exam 2 and 3. It's like 1 and 3 or 1 and 2. So this is that line in your grades page inside web courses is what you want to look at. Now, I haven't updated homework. Actually, we haven't had any homework. So the homework, your homework pointage inside web courses for now is still the same. All right, so that's out of 36. So add that to whatever you have, best 2 out of 3. The clicking pointage should be different. I haven't updated all of that to as of today, of course, because we just did a clicker question for today. All right, so that pointage, so you can use that pointage, which was the first week of November, as an estimate to estimate where you stand going into the final. All right. Now, hopefully over the weekend, I'll have some time to update the clicking pointage. And then you'll really have a good idea what you have going into the final. But don't forget, for all in the sound of my voice, including the ships at sea, we have more homework ahead, we have more clicking ahead, and we have a final exam coming up. So let's talk about the last few weeks. All right. Now, here we are up here, session 35. That's today. And what we're going to do today is talk about lenses and ray tracing for lenses and kind of a model of eyeglasses and microscopes and stuff, telescopes. We'll do a few examples of that in just a few minutes. Next week, we have session 36, 37, and 38. Okay, and we're going to be studying chapter 27, and that's wave optics for 36, 37, and then 38. All right, so go ahead and make a note of that. That'll be your study assignment for the weekend. Just start finish studying chapter 26 on lenses and stuff, and then dip forward into wave optics. Chapter 27. Then after that, we have 3 more lectures. Section 39. We don't have any class on the Wednesday before Thanksgiving, and that's university-wide, which is unusual. That's true. Yeah, it's university-wide. What? Yeah, this is the first. This is unusual. Usually we have classes that day, but UCF, you know what happens? A lot of instructors, it turns instructors into like Dr. Jekyll and Mr. Hyde, two mental states for instructors. State number 1, Dr. Jekyll gives the students the Wednesday off. State number 2, Mr. Hyde, the maniac, gives exams on that Wednesday. And so students are forced to come to, so UCF is usually like a ghost town on that Wednesday before classes. So this is the first year that I think as long as I can remember, going back to 2002, that they've done that. So, but we do have 39, 40, and then the last day of class is 41. Now here's another one for those of you that are new here. Another thing that we don't have this semester, and actually for everybody here, we don't have a study day. We go from the last day of classes on the 4th right into final exam week. So you guys are going to be, possibly some of you will be taking exams on that Thursday. And then here's our date, on the Friday, the 6th of December. So we do not have a whole lot of time. I recommend, we don't have, a lot of times it's just the luck of the draw, when your exam falls, the way that, I don't know how they set it up, but sometimes it's like at the end of exam week, and then everybody has a lot of time to study and get ready. But this time, bang, we're the second day of exams. So and no study days. So it's even worse than that. So anyways, the last day of classes, session 40 and then session 39, right in here, we're going to be studying um, periodic table and hopefully a little bit of quantum physics, i.e. the atomic spectrum of hydrogen. We'll at least get a little handle on that. And hopefully that will bring it all together. In fact, all of 2053 and all of 2054 will be bringing concepts during that last 3 sessions. Now, the other thing that I normally do, last day, last class, last lecture, I take half the lecture and give everybody a mini review on paper that I'll give you a handout and you'll click in your answers. And it'll be for bonus points. Okay, so you might have 20 or 25 questions, maybe 1 or 2 calculations to click in an answer. And it will be it'll be self-paced like on an exam. So I'll give you it on paper and you'll go at your own pace. And you can study with your neighbors and stuff and just work stuff out, which is good. So, and that'll be the last day of classes, session 41. So I don't know, like the last hour or something for that. And then you'll be able to do that. Then the other thing that I normally do is a second bonus point activity for those of you that are a little bit nervous about your grade, a second bonus point activity, and that's just like a big mega review homework in web courses due on the, first, 6 a.m. on December 6th. And I'll probably open that up sometime on maybe the 3rd or the 4th of December. So so you can do that, and you have a bunch of attempts. And both of these, however, go by percentage. So they're not participation. The last day of classes, that's not going to be a participation. It's going to be how many you get right. So you want to get them right. And the homework, always, you want to get that right too. All right. You want to get on the scoreboard with those, because even if you don't get perfect scores on either of them, you still get a little bit of bonus pointage. Okay. So usually I make it somewhere between 0 and 4 bonus points. So hopefully that'll, help out your grade a little bit in case you got a little bit of stinkiness and, I'm not looking at nobody, but I know some people have a little bit of, well, embarrassment on their grades. And so, but that'll help out a little bit. All right. Now, one thing I want to emphasize to you, the final exam is cumulative. 7 a.m. sharp. If you're not here before the first person leaves and deposits their test, you are SOL. That's an old Latin phrase for toast. You are toast. All right? Any what? No, but if you have attempts on your homework, you can review all your attempts and then coordinate with your friends. Do you have some friends in this class? I mean, to study with? No? Everybody, you're not distributing the Chick-fil-A nuggets sufficiently. But anyways, so just tell them, I'll have my study group at Chick-fil-A. I'm buying, and then you'll get plenty of friends. But anyways, Benjamin, if you have attempts, you can go back and I'll make sure you can look at the attempts. I think they're still open. You can see whatever attempts you have and kind of work out the answers again if you need to. To Breeze. Sometimes you sit over here, right? No, you always sit there? Okay. To Breeze. No, Faraday's was 9. IX. Formula 9. Look all the formulas. Huh? Yeah, it's a Formula 9 on the matching. Yeah. Yeah, Roman numeral 9. And then Roman numeral 8 was, you know, element of flux. All right, so be here at 7. We'll temporarily suspend. Now, I'm not going to record it on the, in case I get nabbed by the dean or something. But where's that sign?
It's right here. It's knocked down. The no
Oh,
one.
yeah, there was a sign up here that said you're not supposed to bring certain things. Oh, this thing up here, we're going to suspend that from 7 until 9:50 on December 6th. Okay, so if you had to bring, no, I'm not talking about Chick-fil-A nuggets. I couldn't eat that kind of stuff at 7 in the morning. You kidding me? But in case of coffee or whatever, just don't make a mess. Anyway, now students, I'm pretty serious about this admonition. That's why I asked Professor Galileo to have a word because he's the BOSS. You don't want to mess it up. You can mess it up by being late. You can mess it up by not studying. It is cumulative. That means everything up until the last session. Okay, so whatever, the first half of session 41, we're going to be talking about, atomic spectra probably, or maybe the Heisenberg uncertainty principle. But we're going to be talking about that stuff Wednesday, and then you're going to have questions on it on Friday. All right, it's cumulative all the way back. Now, guess what? Because this is physics, it's also cumulative of physics 2053 in terms of energy. So, maybe review some of your concepts of 2053 for energy. Forces. Oh, and guess what? The two isolated source charges, figure out the electric field, magnitude and direction. Remember, we've spent like a week restudying that every day. So it's all going to be, so just study your brains out. And I would start now if I were you, actually. So now if you don't believe me about this schedule, just look at this. This is the official registrar's website. So go to the registrar's website and then go to the academic schedule. And then at the bottom you can see, and actually this website you can look at the schedule for any of your classes. Just put in the first thing, class meeting pattern. So that's like Monday, Wednesday, Friday, Tuesday, Thursday, whatever it happens to be, and then the times and stuff, and you'll see. So that's what it is for us. And one day, I have a wish that I'm going to propagate into the future. Everyone in here, unlimited potential. Plus you're young. You have all your life ahead of you. If the day comes that you were elected the mayor of UCF or the governor of the great state of Florida, I want you to think back to Dr. B and give me this one revenge. I want you to ban from the entire state 7 a.m. finals everywhere under penalty of law. 30 days of bread and water. For any university that schedules 7 a.m. exams. And why is that? Because I hate them. All right. All right, let's talk. Okay, my wonderful students, we're going to do some sketching and stuff and calculating. We're going to talk about lenses. Now, this is an image of a Carl Zeiss lens from Germany. These are like the best lenses you can get in the world. And I actually have, this is one that I own for my camera. It may look like a small coffee cup, but it's actually a lens. And the optics of the Zeiss system is superb. And for many years, they were made in East Germany, and they were very expensive to get, but you could get them. And they had a car when after World War II. Before World War II, they just made them all over Germany, various factories. And then World War II, they split East Germany and West Germany, which is, you know, like history's for you guys. But back in my day, they were still East and West Germany. And the camera lenses were over in East Germany, I think. But you could get them. And I got one. And they're superb optics. So versus this thing, you know, like my specs up here. Take a look at this. Okay. Look at this. My cheaters that I got at Walmart. Okay. Heinous quality optics, but they're good enough to read with. Those things, you can read a page of newsprint on the moon just about with how good they are. Now, the guts of those things looks like this. All right. It's what you call a compound optics or a compound lens. Now look at that. You've got the first one is what you would call a convex or a plano convex, I guess. The other one's double so look at all those lenses. All right. Now the front end is up here. This is the objective. This is the what you would call the objective lens here, and then this one's the, you know, you could call it the eyepiece. Your lens, your film or your charge coupled device is back here if you have a digital camera. So what is that? That's 7 lenses. Now we're gonna start with one lens, and then we're gonna stack up 2 lenses. But I mean, you know, you study optics enough, you'll be able to savvy this stuff. And it is an enormous. I mean, you know, getting a PhD in optics is a serious undertaking. You can just look at that. And some of those lenses are actually made of 2 different kinds of glass. So it's, if you look at them, you know, it's like that top one might be 2 different kinds of glasses that they shape exactly in that shape. Very complex. So what we're going to do now, we're going to go to the document cam, and you know what, my Talking PDFs notebook and software crapped out on me, so we didn't really have any Talking PDFs from the last time. So we're just going to go back to the standard on paper document cam workouts. Go ahead and switch over. All right. All right. Now I've got some. Can you find a pencil sharpener and go sharpen that? I'll try to use this stinky one I got in here. So if you have some graph paper, get it out. And I've got some up here. And what we're going to do is, oh, you know what else? Try to get out, if you have a graph paper or not, try to get out a straight edge. Boy, this thing is just, how come this, okay, that's better. Okay. Try to get out a straight edge if you can. Now, what I'm going to use for a straight edge is the card from inside my calculator. All right. Ooh, nice. Actually, 5-finger discount, I'll use this. Thank you. Appreciate it. Okay. So here's what we're going to do. We're going to make, I'll give you a freehand sketch of what we're going to do on graph paper. We're going to make two similarly slanted surfaces with of a glass lens surrounded by air. Okay, so you can make a little sketch of that. And we're going to be very careful about the slope of these two surfaces. We're going to make them, rise over run of 3/1. Okay, and this is going to be a rise over run of negative 3/1 on the other side. And then we're going to send in some rays parallel to the optic axis and then diffract them through and calculate the angle at which that thing exits. So we're going to be doing two different refractions. So this is going to be N1 out here, and this is going to be N2 over here, and N3 over here just for bookkeeping, and N4 out here. N1 and N4 are the same, N2 and N3 are the same. But we're going to have two different refractions, so we want to have two different dealy bobbers there. Okay, so now let me set this up and do your best. Let me get my specs. It is? All right. All right, so unfortunately this, you know what this is? It's a flashy thing. And flashy things, you know what those are? They're neuralizers. So don't look at that screen over there or you'll get neuralized. Just like in MIB. Okay, use those two screens over there. All right, so what I'm going to do, see if you can follow me here. I'm going to pick a dot up here, and I'm going to make up 3/1 line here. So what I'm going to do is go down 3/1, down 3/1, and that'll be pretty good. And I'm going to make my surface like that. Okay, and then I'm going to dip across here, and let's see, let me dip across by 6 blocks. Okay, so I'm going to do the same thing, only it's going to be drop 3/1, drop 3/1. Okay, so these are the same tilt angles, and this lens, okay, so there's the shape of my lens. All right, now we got stuff up here above, and we got stuff down here below, but we're just going to look at this one. So we're assuming that the lens is thin enough that this small slice of the lens is going to contain the one ray that we send in. All right, so now I'm going to use my blue ink pen. Actually, let me use my red. That'll show up nicer. All right. Now I'm going to send mine in right here in the middle. And I'm going to send it parallel to the optic axis. So this is coming straight in. From the left. Okay, so that's parallel to the optic axis. Now I'm going to construct at this point a perpendicular line. Now what the perpendicular line has to be the negative reciprocal of the slope. So this one has a slope of 3/1. The perpendicular line has a slope of negative 1/3. So that means up 1, back 3. So here's a dot. Okay, and that's going to be my perpendicular, my normal vector for this surface. All right. Okay. And I'm going to run that out here a little bit. So this is going to be theta 1, my angle of incidence. All right. Now, a couple things. This horizontal line here, I'm going to erase it in a second. But this little one here, going straight across, the light ray does not go there. All right, that's the no line. Okay, it's going to bend away from that and towards the perpendicular. All right. Now, so I'm going to put my outgoing line. Okay, so this is 3 to 1. So let me put my outgoing line. I'm going to put it out here, right about here. That's 1 block down and 2, 4, 5 blocks over. Now you don't have to do it the same way I do, but all right. Now here's the refracted. Okay. Now let me extend. All right. I'm gonna erase the no line here. Okay, because I'm going to need every inch of space I got here. All right, so I'm going to extend my perpendicular now. And I'm going to extend it about halfway across. Okay, now this angle here is theta 2. All right, now try to label it neatly if you can. We're going to get real cluttered up here in a few minutes. All right, now we can figure that out. We know what to do with that. All right, and we can actually figure out theta 1 as well. And to do theta 1, let me go up here and do a 6 by 2. So here's my Here's my 1.3 triangle. So this is square root of 10. So this is theta 1 right there. So the sine of theta 1 is fairly easy. It's 1 over square root of 10, which we'll calculate that in a minute. All right. Now what we want to do is figure out theta 2. For that, we need to know our indices of refraction. So let's make some notes over here. N1, this is going to be air. And down here, N2, let's call it 1.500, just a nice round number. So that's going to be some glass. That's typical area for glass. All right. So now we can figure, we've got the theta 1 here, the inverse tangent of 1 over square root 10. And so actually we don't even have to do that. We just got to put this in there. And so we can find sine of theta 2. So let's do that. Okay. And this is at our first interaction. So first interaction. Okay. So N1 sine theta 1 equals N2 sine theta 2. As always, okay, so we have 1.000. Now sine theta 1, I'm going to put in 1 over square root 10. Okay. And then N2 is 1.500. And then sine theta 2. So sine theta 2 is what we want to figure out. Now the hard part is going to be figuring out over here what the angle of incidence is over here at the second interaction. But we'll get it. Don't worry about that. We're going to get it. Okay, it's a real dance. Okay, so sine theta 2 is just equal to 1.000 in the numerator, and then 1.500 square roots of 10 in the denominator. Okay, and so let's see. And that's the same as basically 2 over 3. This is even easier. 2 over 3 square roots of 10. What do you get for this value here? 0 point, 0 point what? So this is going to be about a 9 down here. 2 over 9, so that's going to be about 20 something, 0.2 something. What do you get? Come on, get your rigs out. Yeah, 0.21082. Okay, so theta 2 is equal to the inverse sine of that. So what do you get for inverse sine? Anybody verify 12.17? Raise your hand if you verify. Okay, 12.17. And let's give it 4 significant figures. All right, now that's theta 2 up here. All right, now we got some problems. So we got to figure out the angle of incidence over here at the second interaction. All right, so what I'm going to do is go over here to the second interaction point, right here. I'll put a dot here. And now what I'm going to do is try to do left 3, down 1 for the perpendicular. So let's see, that'll be about here, 2, 3, and then down 1 is right about here. All right, so you can visually estimate it. Now we're getting a little bit out of the precision, and we're into mental visual estimation, but still pretty good. All right, now here's the second perpendicular for the second surface. So now down here, this angle is theta 3 down here, and I'll darken it in a little bit. Okay, there's theta 3. All right. And just so you know, here's the second no line. Just extend the red straight on through. Okay. So this is the second no line, and I think I'll leave this one in. Okay. Now this is going from fast into slow. No, it's going from slow into fast. So it's going to break away from that line. So now this is where we're going to have to eyeball something in and then let the numbers do the talking. Okay, so go to your no line and just kind of make a little bit of a bend. No, wait a minute. Let's figure that bend. We can figure out the bend. So let's leave that alone for now. Okay. Now we've got this set of trapezoids and triangles. Now the key is this triangle right here. Okay. This guy right in here. I'll put a little circly blur there. Okay, now the sum of those angles adds up to 180. But we don't know what all those angles are yet, but we're going to get them. All right, so what I'm going to do is go down here and make a little bit bigger version. Okay. Okay, so there's my, no, that's not right. I want this to be slanted. Okay, I'll still put this down here though. Okay, so I'm going to put, let's see, here's the, actually, we're going to need this triangle. We're going to need the no line up here, it turns out. So let me trace that in a little bit. So there's the no line, the first no line. Okay, so I'll do that one straight across. Okay, so here's the first no line. Okay, we're not on, man, that sucks. Okay, try to get this good here. Okay, so here's the no line. Okay, so that's the top of this upper triangle. We got a couple triangles that we got to savvy here. But you know, we can figure this one out. We can figure out this angle. Basically, it's going to be, because this one here, let's see, this angle here is this angle here, right here, is theta 1. Okay, so that's 12.17. So this one is going to be 71.83 degrees right here. Is that what I got? No, 71. So this is 12. Are you sure that's 12.17 here? Okay, that's theta 2. Oh, yeah, so so theta 1 was, what is theta 1? Let's do this. What's sine of theta 1? Or what's the, okay, this one's 18.43. I already did this one. Okay, so sine of theta 1, that's not right. So theta 1 is 18.43 degrees. Okay, so that means that this one is 71.57 degrees. Okay, so that's this angle up here on top of the first no line. All right, now we've got another line dipping below that, and that's and I'll write it in red. And this is the one that we kind of estimated. We don't know exactly what this is, but we're going to let the numbers do the talking. And then we've got the perpendicular. This is 71.57 over here as well. So we have this angle. We can figure that one out. Well, we don't know the other two acute angles in here. But what we do know is that the perpendicular line, the normal line, my key triangle, is a combination of this perpendicular and I'll run it out about to there. And we go from here, 1, 2, 3, down 1. Okay, so this one, all right. All right, now, this is my key triangle here, all right? So I'll label it A, B, C for bookkeeping, all right? Now, this is a right angle here, so this is 90. So it's a perpendicular line. This is a 90-degree angle, so that's a perpendicular there. That's going to help us. Right, now this one we know. This is 12.17. That's theta 2. All right. Now here's what we got to do. 71.57 plus 12.17 plus this guy up here, I'll call it alpha. They have to add up to 90. All right. These three angles, 12.17, mystery angle alpha, and 71.57, those have to add up to 90. So alpha is, verify me on this, 6.26. Anybody verify? Okay. All right, so now let's go over here. This one, this angle up here on just below the no line is what's 180 minus 71.57? That's equal to 108.43. Anybody verify me on that? Okay, so this one, and I'm not going to write it in. I'll do it like this: 108.43 degrees. All right. Now we got the alpha as well. Now let's add up 10. Now this angle here, I'll call it beta. Okay. Beta plus 108.43 degrees plus alpha, which we know it's 6.26. Those add up to 180 degrees because it's the interior angles of a triangle. It's an obtuse triangle, but we got it. All right, so 180.43 plus 6.26 is 964,114.69. So 180.00 minus 114.69 is 31 5 6. Is that right? Anybody verify me on that? 65 point. That can't be right. Let me do it on my calculator, my calculator. Let's see here. Okay, 108.43 plus 6.26, 114.69 minus 180, 65 point. Okay, so this is, so beta is 65.31 degrees. Okay. Now, my angle of incidence is right here. I'll write it in. This is theta 3. All right. Now, beta plus theta 3 equals 90 degrees. All right. So let's see, 90 minus 65.31. Anybody verify me on this? 24 theta 3 is equal to, what do you get? Anybody verify me? 24.69. You got it? Who verifies? Okay, good. All right. And there's our angle of incidence for the second interaction, right? Now, I know this is painful. We've done a lot of scratch work here, but, you know, in practical terms, you would do this on a computer. You just train a computer to do all this stuff. Because you could do, you know, the other thing we could have done is do equations for each of these surfaces. You know, x plus, you know, y equals mx plus b and solve it all algebraically, but that'd be a pain in the neck. This is just as good. Okay, so now n3 sine theta 3, which we now have, equals n4 sine theta 4. All right. Now, the no line, the second no line is right parallel to this interior red line. That's the actual light ray. Okay. So my outgoing red, I'm going to do it in the upper diagram first. I'm going to dip it. No, wait a minute. Let's actually figure this out. Let's figure out what theta 4 is. Okay, so N3 is 1.50, and sine of theta 3, 24.69 degrees equals 1.000 times sine of theta 4. So sine of theta 4, I'll use my big pencil here. What happened to the, so sine theta 4 is equal to 1.500 times, what's the sine of 0.41771 equals sine theta 4. Okay, so now inverse sine of that. Wait a minute, sorry. Twenty-four sine 24.69 times 1.5. Okay, so this is equal to, verify me on this, 0.6266, no, 62656. Anybody verify me on that? Okay. All right, so the inverse sine of that is 38.7.80. Okay. So that means that if I go up here now, I don't want to go 45 degrees away from perpendicular, maybe a little bit less than that. So let me go, here's about a 45. So I'll just go I'll go right through this dot here. And we'll do that. Where's my, okay, so here's, and I'll write this in red, theta 4. Okay. I'm not going to write theta 4 down here, but we calculated it here, so, all right. Now, what's the lesson of this? The lesson is that if it comes in parallel to the optic axis, no matter what happens, it's going to converge on the other side, and it's going to converge to a focal point. All right. And so the shorthand of this, let me pause for questions before we continue. Any, CJ? This one up here, or are you talking this triangle? This one? Oh, over here? That's a 3, but that's the slope of this. That's this triangle here. I made it a 3, rise over run, rise 3 over 1. Okay. So I need that angle to figure out a bunch of other stuff. All right. And that's going to be equal to theta 1. So this slivery angle here, theta 1 here is the same as theta 1 over here. So if you do your trig, all right, as long as this line here is perpendicular to the lens surface right here. All right. Another question. Okay, I want to give you a small sketch now for the lesson here about convergence. The shorthand approximation is simply this. You draw on your optic axis. Then you place your lens as a straight line segment. And this is what we call the thin lens approximation. Okay, now for a real physical lens, at the Carl Zeiss company, you wouldn't do this approximation, except if it's just for scratch work. Okay, they would use very fancy computer programs, or back in the old days, a ton of people calculating sines and cosines out the wazoo to do this. But the shorthand for a thin lens in parallel out through some focal point, wherever it happens to be. I'll put my focal point 8 units out. So here's my focal point, and that's where the ray goes. All right. So here's my object out here, my little arrow. Okay. Second one, center. This is point S, symmetric point. In other words, the center of the lens. Okay. Through the center, just keep going straight. Okay, so this one's going to go. Okay. Now those two lines are not parallel, slightly different tilts. Okay. And what we do with these lines is we figure out the image location. Now this one's going to have an image location way back here because I'm very close to the other focal point. So here's the near focus. Okay. Okay, 8 blocks west of S. So this is F2. This is F1. All right. So this is the shorthand. And if you look in chapter 26 on lenses, you'll see a list of the 4 principal rays. This is 2 of them. Now there's another one that if you go in through the focal point, it comes out parallel. All right. So that would be this one. You know, my image is a little too close to the focal point. So my incoming through the focus, if my lens were this big down here, it will come out straight. But we can't do it on this sketch. Okay, but we're going to do it on another sketch. All right, can you change to my next slide? All right, so let's do a thin lens. Diagram. All right. All right. So now we're going to do a lot of sketching. All right. So go ahead and draw your optical axis and draw a thin lens. And I'm going to make my thin lens 3 units high and 3 units. Actually, let me put it here in the middle. Put it towards the middle of your paper. So here's my thin lens. And we're approximating 2 interactions that which we could calculate it out, collapse to 1. All right, so, and that's basically at the thin lens. All right, now, let's say that the focal length is 4. All right, so let's put f1 and f2 at 4. Now let's go way out here past, let's go out 4, let's go out 10 blocks here. So here's my object location. And I'm going to draw an object 2 units high. All right, now this will work. This should work out to pretty good. So here's 4 blocks here from the symmetry point S to F2, 4 blocks from the symmetry point to F1. All right, so let's do one of our first rays. Okay, incoming parallel. And it dips down to focus F1. So here's our, that's the one that we just calculated, the 2 surfaces, 2 interactions. And here's the approximation. And just run your ray on out. Okay, so there's your first one. Now let's go through the symmetry point. Okay, I like to use this one because it's easiest and cheesiest. All right. So from the top of your arrow through S, and this one, okay, let me move my name here. Okay, I'm going to put F1 up above here. Okay, so here's my second ray. Okay, so I'll label this number 2, and here's number 1. Okay, so right here is my image. Okay, so put a dot where those 2 rays intersect. Let me make this. Okay, and here's your image location. Now it's upside down. And it looks to be about 6 point something blocks to the right. All right. Now, let's try an experiment. I don't want you to do this, but I want you to see it. So watch what I'm about to do. I'm going to draw a third line. And it's going to come out, I'm going to go through F2 and then come out parallel, but it's not going to intersect directly at this dot. It's going to miss it by a little bit. All right, so here I go. From the top of the arrow through F2. Okay, now it intersects the thin lens here. So now it goes straight out to the right. Oh my goodness, this one's not too bad. I made my dot really nice and big. I'll just draw it in dotted line though. As a caution that when you do this, you know, this one has nice agreement for the 3 rays. So this is ray number 3 up here. That's pretty nice agreement, but you don't always get that. If I was to do it sideways like this and make it this big, you'd see a little triangle form right here with these 3 rays that they don't always meet. And that's where the thin lens approximation breaks down. You get a little bit of what you call aberration, a little bit of fuzziness in your image. But good optics compensate, and that's why you have that fancy Carl Zeiss lens to help you. All right. So this is a thin lens approximation. Now, one of the nice things is 1 over f plus 1 is equal to 1 over d0 or do plus 1 over di. So let's see if we can figure that out. So my focal length is 4, so 1 over 4 equals 1 over 10. This was 10 blocks out, 4, 8, 10, and that's equal to 1 over di, or pardon me, that's a plus sign there. Okay, so there's 1 over di. So 1 over di is equal to 1/4 minus 1/10, which is 5 over 20 plus 2 minus 2 over 20. Okay, so that's equal to, so 1 over di is equal to 3 over 20. So di is equal to 20 over 3, which is 6 2/3 blocks. And that's about where we are here. So this is nice. 6 2/3. So our diagram's not too bad. Pretty good for government work. All right. Now there's a couple other things. You know, this one, the image is smaller, notice. This one's 2 blocks high. This one's 1 point something blocks high. There's another equation in there in the textbook for figuring out the magnification. And it's a little bit complicated, but I'll go through that with you on Monday. In fact, we're gonna stop here for a minute, and I'm just trying to think if I should give you a homework over the weekend. Oh no, it's Cassandra's birthday, so okay. And, hey, whose birthday is it today? Or who's has a birthday over the weekend? Cassandra, I didn't see your hand go up. Yeah. Okay, happy birthday to you. Happy birthday to you. Happy birthday. Happy birthday. Happy birthday to you. Switch over to the dock cam or to the computer. All right, we're not done yet. Hey, that's my wonderful students. That's an essential part of instruction on optics. Singing happy birthday. Everybody knows that. Anyways, we just did the thin lens calculation, very basic. What we're going to do on Monday is a telescope, and you know the way a telescope works. You have 2 thin lenses, and you make it so that their focal points, they can be different focal lengths, but the focal points match, and that's perfect for a telescope. That's what Galileo did. We're also going to go and take a look at a microscope model, and that's a little bit fancier. Go ahead and look in the microscope section. We're going to go over this diagram and then do a microscope calculation. So that's basically this. Study chapter 26.4, 26.5, and then dip into chapter 27 up to chapter 27.5. All right, now you're dismissed. If you want to come up and get your test, we got them up here. And Andrew, can you give out the tests? Andrew has your test if you want it.
Scantron or just the regular test?
Just the